In this, the final section of our classes exploration, we're going to touch upon a number of different areas, from casting to looking at the relationship between classes and structures, to the use of the what's known as the this keyword. And we'll start off actually looking at this. This is quite an interesting one. I've included it here because it highlights an important aspect about how the code that we write gets to be executed. And one of the challenges that, if you like, is faced in terms of compiling languages and making sure methods can call appropriate, access appropriate member data or items like that. You have it. This is available as a keyword within C++, within Java, within C#. So generally, it's there within quite a wide range of languages. It's also the type of keyword that is very, very rare ever to really need to use the thing. You would generally use it simply by way of providing a bit of clarity, really to the viewer of the code as to what is intended. So, by way of introducing what this is, let's do a little bit of a setup. So we can assume, you look down at the bottom right, we've got a class called foo. It has some data that it stores, and it also has some methods that it associated with the class 2. And line 3 and 4, we create 2 instances of foo on the heap in this particular case. Now, we said that when we create an instance of an object, in this case using the new keyword, it's something that gets to be stored on the heap. And down here you can see when we look at the heap that we're saying that A's data members and B's data members, in this case dat, is stored on the heap. We also highlighted that for the executable instructions, the code that we write, it too is stored in memory. Generally at the start of the memory is allocated to our program, and this contains the machine instructions that get to be executed. For this class foo, it also contains the instructions associated with the do work method. So whenever we create an instance, for example on the heap, the only thing we're storing on the heap is the actual data members. For the instructions that specify what it is the methods within that class do, they're all stored in the code section at the start of our data. Now that's good. It's efficient, because we do not want to, for every instance, have to store all of the data and then to duplicate all of the machine instructions. That would be needlessly expensive. But it does introduce an interesting challenge. So for the instructions that we have within the code, so if you look now at do work, okay, it doesn't take any properties, but it does something. If we were to go to those instructions, and as part of do work, we want it to read the value of dat, or to manipulate it, how do those instructions know which value to access? So when you call the do work and the instructions in the code, is it A's? Is it B's? How do those machine instructions actually work out the things that should be accessed? How to do that is that you actually have a hidden variable. It's not that hidden because you can access it. It's the this variable. So there's an additional variable that factors into the methods, and it points to, it addresses or tells that method where it is that the data that it's working on is found. So effectively it links the method into be it A or B's data. So effectively this additional semi-hidden parameter is the address in memory of the data of the instance of the instance of which we're calling that method on. So do work will be called in A's, or do work will be called in B's. And the parameter we pass in is either a pointer to A or to B. And that pointer then enables that method to operate on the appropriate clunk of data. So it's a semi-hidden argument. A little bit under this here, it only applies to non-static methods. If you have a static method, so this is one that can be called from any instance, it can be called outside of an instance. In that case, there is no hidden parameter. It's just whatever it is you specified for that static method. If it does work in an instance, then there will always be this additional pointer that gets to be passed in to enable the method to know which instance it is working on. And that officially is known as the this keyword. Nice thing about it, it's inferred, so it's there, it's passed in, and if I just did dat on its own, dat plus 1, then the inference of this here is the this dot dat is the ones associated with the one that we're modifying. Where you might want to use this and where you might see this being used, if you're calling a method where, let's say, you're copying data from another instance into this instance, sometimes for reasons of clarity you might sort of see some calls to other dot whatever and then this dot whatever, just by way of differentiating or being precise about, or I mean, it is precise, but being more clear to the viewer as to where and what things have been copied to and from. Casting is the next thing we want to have a look at. We've looked at this already in terms of primitive data about how we can convert an int to float, or an int to a boolean, or a character to a boolean, or things like that. This one here, we're interested in converting an instance of one class into an instance of another class. To a certain extent, this we have introduced. We said earlier on that C++11 supports 4 different forms of casting. You see them here: static cast, const-cast, dynamic cast, reinterpret cast. And we sort of said that static cast, that was your basic, works most of the time. That's the one you normally want. We'll have a look now at the other forms, because where they are useful, and in some cases these things are not particularly useful, but where they are useful, it is in terms of manipulating and converting one object type into another object type in terms of our classes. We'll start off with const-cast. I have an example of its usage here. So let's assume at line 1 we have a method foo. It takes in a character pointer. And in line 3 we have a character pointer, but it's constant, so it's name. So we effectively have a read-only name. It's a string, but we're saying, the programmer has said, nope, this is constant. It is read-only. It is not to be changed. At line 5 we have something which will not compile. So there we're calling foo, and foo says, I want to have a character pointer. Now that character pointer, it's not const, so it's allowed to obviously read from it, but also to write from it, to change it. So foo says, I want to accept in a pointer to an array of characters, but I want to have the ability to write to them, to read to them, whatever I want to do. Line 5, the compiler quite rightly says, hold on, name is read only. So I can't pass this into the method, because if this method is expecting to change it, then we have a problem, because name only is defined as, name is defined as a read-only data item. Line 6 is how we can get around this if we really want to get around it. The const-cast, we can use it to cast away the constness of a variable. So what we do in line 6 is that even though we have a constant char star, something we're not allowed to change, in line 6 we basically cast it just to a char star. We get rid of the const bit, eradicate it. And then the compiler goes, okay, we've done this casting of name, I now have something that is just a char star. I can pass that in, and I pass it in to the method. So it enables you to effectively ignore if something is constant. I sincerely hope at this point you're going, oh, this is not a good thing. And you're right, this in 99.9% of cases is not at all what you want to do. There is one rather specialist reason why you might want to use this. And the reason is not a particularly good one. It comes down to, if you're dealing with third-party code that you have 100% confidence in, but it hasn't been designed particularly well, then you might consider using a const-cast. In particular, if the third-party code, it has a method, and you are 100% certain that that method will not change the data. So it's definitely not going to change it. But the creator of that method, even though it never changes it, didn't bother defining the parameter as a const parameter. And remember, if you're creating your own methods or functions and you don't change something, you really should declare it as const by way of one of the property types, because that makes it explicit to the callee and also increases the ease of use, because I can then pass in a normal or a const parameter to it. So if you have third party, you know it won't be changed, but the developer neglected to actually say this by way of the signature, then in that case, and you really must call this method, you can use a CONST-CAST to do that. That's about the only case. Beyond that, never really use this. You shouldn't use it. Next up then is static cast. So this is the one that we have sort of looked at a little bit. We'll look at it a little bit more here. It can be used to perform type conversions that are legally supported within C++, that C++ thinks are valid. Now, this, as we've seen, this includes us casting from one type of primitive data to another, but it also involves casting from one class instance to another type of a class. And to do this, the constructors that we define are key. And in particular, if we say we want to do this type of cast, the compiler, when it's generating the code, is going to look to see, is there a suitable constructor that it can call to perform the conversion. And we'll show an example over here. So let's have a look at class A up at the top. It has a single default, no argument constructor, nothing else. Class B, we actually have two constructors within B. We've got a default constructor, and we also have a parameterized constructor where if you give me an instance of A, I can use that to create an instance of B. Lined just under that then, we have two methods, foo A and foo B. Foo A takes in an instance of A, foo B takes in an instance of B. So this is what we have. So let's have a look then at the code at the bottom. So line 1 and 2, we're creating an instance of A, creating an instance of B, fair enough. Line 4 won't compile, it's problematic. We say here we want to call foo A, but we want to pass in B. So the compiler will say foo A takes in an instance of A, but you're giving me B. I can't convert a B into an A, because whenever it then goes to look at class A and it says, okay, can I create an instance of class A if I have an instance of class B? It looks at A's constructors and goes, nope, there's nothing there that can enable me to do that. So it crashes, or not crashes, sorry, it ceases the compilation at that point. And line 5, if we try to force the matter and we say, actually, we want to cast B into an instance of A, it will also throw up an error. It will say, okay, if I go to A, I don't see any constructors that enable me to create an instance of A using an instance of B. So again, it stops at this point. In line 7, we're swapping it the other way around. We're calling foo B. So foo B expects an instance of B. But we are passing in an instance of A, and we've requested that we statically class A into B. What will happen in this case is that part of the compilation process will go off to B. We'll have a look at the constructors that are defined within class B, and we'll ask, if I have an A, can I turn that into a B? And in line 5, we have a constructor that enables us to effectively do that, that if you give me an A, I can build a B. So what the compiler will be saying then is that, yes, that's perfectly fine. I will go I will take A, I will go and I will create an instance of B. Now, this is an R value B. It's not one that we can directly access. It's a temporary variable that gets to be created and passed around and then discarded. So it's an R value. And I will pass this into foo B, and it can be quite happy about it. At line 8, it also works. And this gets at the point that this type conversion is implicit. In the same way, when we had a look at casting between ints and chars and bools, we saw that it happens automatically that if we have a boolean, we can automatically convert it into an int without us explicitly saying that. This also applies to static casting from one instance of a class to another instance. We'll automatically look at the constructors and if there's one that's defined, we'll assume that's what was meant, and we'll then execute it. So 7 and 8 are equivalent. Quite often 7 would be used simply by the programmer by way of indicating that, look, I'm doing an explicit cast here. I want to make it clear to somebody else looking at it, but functionally they have the same outcome. Static cast, we can also use static cast for casting up and down within a hierarchy. If we have base classes, refined classes, we can use the static cast to move up and down that hierarchy. Now static cast, because it is done at compile time, so it's there's no extra overhead at runtime, so it's a fast way of doing this. You obviously can't perform runtime type checking. So it's always going to be safe to say, here I have a circle, I want to treat it as an instance of shape. If you're going that way, that's no problem. But if I have a shape and I say, actually I want to treat it as an instance of a circle, that is more problematic because maybe that shape is a circle, maybe it isn't. The only way that you're likely to know is actually to test it fully at runtime. Now, you can use static cast if you want to, if you're concerned about performance and you know that definitely this is going to be the case. So downcast, they're untested at runtime. It just assumes it must be safe to do this here because it was one thing specified by way of compilation. So it is potentially dangerous. Dynamic cast is our safe way of doing this. So dynamic cast is a runtime check. It will be executed whilst the program is running, not whilst it's being compiled. So a lot of dynamic casting will have an impact on your performance of your program. But what it will do at runtime is check to see if you have an instance of this base class. I've got a shape, and I'm saying, actually, no, it's a circle. It will test at runtime to see if that really is the case. Interesting thing about the dynamic cast is that it is then failable. Same with the other casts as well, but for example, static cast, if it fails, compilation halts. For a dynamic cast, we don't want to halt the program because that's a little bit excessive. Rather, we want to indicate to the program that the cast has failed and the program can take some appropriate action. Now, there's two different mechanisms whereby it does this. You can see them in the code on the right. So if I am using dynamic cast on a pointer, so I've got a pointer to a shape and I'm saying, actually, no, turn it into a pointer to a circle. And I can't do this, then I get back a null zeroed pointer. And I can check my pointer in line 3 and 4. If it's null, then I'm going to trigger some appropriate action. If I'm dealing with a reference, and you can see this in the bottom lines, references cannot be null. They must always point to something. So in this case, we can't null the reference. That's not allowed. So we throw an exception, a bad cast exception, and that can be caught and then appropriately progress from there. Last of our casts is the reinterpret cast. Reinterpret cast can be used to perform casts that are otherwise not technically allowed in C++. So something that a dynamic cast would say, I'm not happy with this. Something that a static cast would say, it doesn't matter. Any of these types of casts, if you're thinking, no, couldn't possibly do this. If you really, really wanted to do it, you could use reinterpret cast. It basically is unchecked. It lets you take a pointer to one object and turn it into a pointer to another object. You can take pointer variables, turn them into ints, do whatever you want, turn ints into pointers. Basically, it reinterprets raw bytes. And whatever you ask it to do, it will quite merrily do. If you really want to do it, and want to introduce lots of nasty bugs in your program, that's fine. It's, I suppose, for the sake of completeness with old style C++, they put it in. But this is the type of thing you really should never ever use. Classes and structures. We'll finish looking at these. You should and you will be aware that that there is notionally a clear distinction between these, that when we talk about a structure, we generally are referring to a clump of data that we are tying together into a composite element into a structure. When we talk about classes, we're generally referring to some notion of an object or an entity or a thing which has some data defining properties, which has some functionality embedded within whatever methods it offers. Within C++, in terms of the rules of the language, there's very little difference between structures and classes. The only sort of main or thing of significance is that within a structure, the method and the data that you define by default is public. If you didn't have a public and a private section, you just defined it as its own, it's assumed to be public. And within a class, if you just define something and you haven't put it into private or public, it's assumed by default to be private. And that's basically the only difference. That structures, it's clear stuff, assumed to be public. Classes, nope, it's private by default unless you make it public. So they're basically identical. You can have a structure with as many constructors as you want, with copy constructors, with a destructor. You can allocate stuff. You can have as many functions as you need. You can basically use them interchangeably. Now, whilst that is possible within C++, just in terms of how they are defined, in terms of practice, in terms of how we use them, we should not do that. We should enforce our notion of that a structure, we use it more or less exclusively to hold data. It is a composite form holding data. And that classes, they are the notion of a defined type, something that makes sense on its own, has a defined identity, has properties, has methods. So do adhere to that, if you like, design decision, even though it's not necessarily something that's enforced at the level of the language. One main takeaway on this, I mean, we've got we've got the classes and structs, there's useful things there. In terms of casting, we had a more detailed look at the different forms. Static cast, dynamic cast, these are good ones, and it's nice to be able to distinguish between when you want the cost of that casting to occur at compile time, or if there is to be a runtime cost by way of safety. The other two, in terms of casting away const-ness or reinterpreting raw bytes, generally avoid.